Hello everyone, this is Mr. Underkoffler. We're going to do a short little video here on sets of numbers. This is a preview of stuff that I'm going to officially teach you soon in a future packet of guided notes. So let's start with the most simple set of numbers that you ever learned since you were little as a kid, counting. These are called the natural numbers. 1, 2, 3, 4, 5, 6, and so on and so on and so on. The numbers you learned how to count with before you even knew that zero was an idea. These are the natural numbers. They do not include any negatives. They do not include zero. They do not include decimals or fractions. Well, as you got a little bit older, you learned about zero, and that is actually a separate set of numbers. It's the same as the natural numbers, except it also includes zero, called the whole numbers. Both of these guys do not include any negatives, decimals, or fractions. Well, then you learn about the negative numbers. And the integers include all of the whole numbers and the natural numbers, but they also include their negative counterparts. So integers are not just negatives. They're all the whole numbers and natural numbers, but also their negative counterparts. However, none of these three include any decimals or fractions still, unless it's a decimal like 2.0 or a fraction like 6 over 1, which is the same as 6. Well, rational numbers include everything we've been talking about. They include the integers, they include the whole numbers and natural numbers, but they are officially defined as anything that has the ability to be written as an integer over integer fraction. Now, that's pretty much going to cover almost everything you've ever seen in your life. Almost everything you've ever seen in your life. It includes whole numbers. You can write them as a fraction. It includes the negative counterparts of whole numbers. You can write them as a fraction. It includes mixed numbers. You can write them as a fraction. Decimals that are terminating decimals, that stop, they obviously can be written as a fraction and sometimes even reduce. Repeating decimals. You learned how to do these earlier. This does not become 8 over 10. This becomes negative 3 and 8 ninths. If there were 2 digits repeating, then it would go over 99. If there were 3 digits repeating, like 0.821 repeating, then it would go over 999. So that's the trick. Kind of like going over 10, but it's one less. That's how repeating decimals work. All of these types of numbers have the ability to be written as an integer over integer fraction, and that is what officially defines rational numbers. Well, let's talk about irrational numbers. They are not possible to be written as an integer over integer fraction. Now, you could write anything as a fraction and put it over 1, but not everything can be written where the numerator and denominators are both integers. Let me show you some examples. The most popular one that we've already dealt with this year is pi. Pi, as you know, is a decimal 3.14, yada, 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 goes on forever. There is no way of writing that as an integer over integer fraction. We're going to soon talk about square roots, which are the opposite of taking a number to the second power. And if you had a calculator with you, which you don't really have to, just take my word for it, the square root of 2 does not have a nice whole number answer. It is a decimal that, like pi, goes on forever, but never repeats. This is key. Hear me out. Decimals that go on forever, but do not repeat, are not possible to be written as an integer over integer fraction, and therefore they are irrational numbers. Now, there could be a pattern like 0.1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, but that's not the same as 0.01 repeating. If you could put a repeating bar over it, then you could put it over 9 or 99 or 999, and then you would be able to write it as an integer over integer fraction. But decimals that are not capable of being written as an integer over integer fraction, which honestly you have not seen many of them in your lifetime. Pi is by far the most popular, but these are the ones that are classified as irrational numbers. Now, we're going to look at some practice problems, and you're eventually going to do some on your own. If you want, you can hit pause in this video real quick, find the guided notes called the Real Number System. Now, we're not going to officially teach those guided notes right now, But if you want to be able to have a similar type of graphic organizer at the top and the information on natural numbers, whole numbers, integers, rationals, and irrationals, you could pull it from this packet of guided notes. But I'm going to keep it here at the top of your screen. I had to shrink it a little bit. At the bottom, we're going to do some examples where we are going to determine what set of numbers the following number belongs to. And I put parentheses S because it might only belong to one set, but it might belong to multiple sets. So, 29. Is it a natural number? Well, yes, natural numbers are the numbers you could count by. You eventually could count up to 29. That's a natural number. Whole numbers and natural numbers are almost identical, except whole numbers also include 0. So yes, 29 is a whole number. And if it's a whole number and a natural number, then it's also part of the integers, which is why I have this graphic organizer here for you to show you every whole number and natural number is part of the integers. So we're going to go ahead and circle Z for integers. Q for the rationals. Everything that's a natural number and whole number is also an integer and is also a rational. And then irrationals, no, they're a different ballgame, which is why the graphic organizer shows them as a separate box. If you could write it as an integer over an integer fraction, then it's rational, not irrational. You can't be rational and irrational at the same time. It's impossible. Before I go any further, if you're wondering why integers is a capital Z, it's because capital I was already taken by irrational numbers. If you're wondering why capital Q is for the rational numbers, it's because real numbers, which is all of these things together, got capital R. So that's why Q was chosen instead for rational numbers. All right, let's do another one together. How about -5? What numbers does it belong to? Is it a natural number? Natural numbers don't have negatives. So, nope. Whole numbers. Whole numbers don't have negatives. Nope. Integers. Integers have negatives as long as they are not decimals or fractions. They also have positives as long as they're not decimals or fractions. So, a -5, yes, it is an integer. Is it also rational? Well, I guarantee if it's integer, we can guarantee it's rational. Now, we can't go the other way. Not all rationals are integers, but every integer is a rational. And if it's rational, then it's not going to be irrational. By the way, the proof for it being rational is that you could write this over 1, which is why it satisfies the definition of rational numbers. Let's do another one. 0.2 repeating. Well, that's not a natural, it's not a whole, and it's not an integer. How was I able to cross them out that quickly? Because those three do not include any decimals or fractions, unless it's a decimal like 7.0 or a fraction like 22/1, where those things would simplify to just a whole number. But something like this, no. But it is rational. Why? Because I can write 0.2 repeating as a fraction. It's 2/9. If it was just 0.2 not repeating, then it would be 2/10, which also would make it rational. So it is not irrational. All right, let's just do two more. -2.31. Oh, there's a decimal, so not natural, not a whole number, not an integer. But could I write this as a fraction? Why, yes, of course I could. It's -2 31/100, so it goes over 100, and that could obviously be made an improper fraction, therefore satisfying the definition of rational numbers. So yes for rational, no for irrational. And finally, one more. The square root of 5. I know we haven't officially done square roots much yet this year, although we did a little bit with Pythagorean theorem. But the square root of 5 does not have a nice whole number answer. It's a decimal that goes on forever, does not repeat. So no, 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 and no. It is only irrational. By the way, if you ever circle irrational, I guarantee the other 4 are not going to be a set of numbers for that. All right, that concludes the short video on a preview of sets of numbers. Thanks for watching. We'll see you next time.